My name is Maeve Revels, and this is my very first time speaking at a conference of any kind. Thank you. That actually helps. So I'm here today to talk about testing legacy code, and I promise you that it's going to be more fun than that sounds. That's why I made the title boring, so I can set achievable goals for myself. Personally, I only touch legacy code when it's absolutely necessary, which it turns out is basically all the time. And I'll be honest, I don't enjoy supporting legacy code, but I really enjoy getting rid of legacy code. It is one of the things that I absolutely love about my job. And I use, thank you, and I use testing to help me do that. So this talk is going to be very heavy on concepts and light on code. I'm not going to make you read any legacy code today. I'm not even going to make you read hardly any test code. I actually had to cut out most of my code examples for time, but that's okay because the concepts are really the important takeaways here. There are lots and lots of resources out there that can teach you how to write tests. I want to cover how to create the right tests for the right code at the right time when you're working under less than ideal conditions. So let's start with some definitions, because in some ways, legacy code's a little bit like that famous description of obscenity, where it's hard to define, but we all know it when we see it. A legacy is something that's handed down from one person to another, and by default, we assume that it's something positive. It could be the key to future success. But it's possible to leave a different kind of legacy, a legacy of pain and suffering, and that's what I'm here to talk about today. So these are some of the words that developers use when we talk to each other about legacy code. It's old and outdated, confusing and complicated, brittle and broken, and just plain bad. So I created this slide from the text of blog posts that talked about legacy code. I also asked people for their own definitions, and my favorite was code originally written by someone else that's currently broken in production. And this is fair. A lot of us encounter legacy code the first time this way. And if you work somewhere long enough, one day that someone else is going to be you. And you're going to feel terrible about the fact that you don't want to get involved. So let's talk about how I overcome that impulse. My name is Maeve Revels, and I've been creating new legacy code for 20 years. And most of it has been in Rails. So this is my first time speaking at RailsConf. My first time attending was in 2007. For the past 3 years, I've been working at AHA. And we've got lots of different engineering roles there. We're hiring for most of them. I'm on the platform team, which is responsible for the system infrastructure. So in the world of DevOps, I tend to land much more on the dev side. I did feature development for many years before I ended up here. And my specialty is refactoring or replacing parts of the system where we've encountered scalability problems. So there's a term that describes exactly what I do for a living: brownfield development. And the first time I heard it, I thought, well, I've stepped in some brownfields. But in reality, just like greenfield development, it comes from urban planning. So a brownfield is any previously developed land that's now contaminated with hazardous waste. Any new development on the land is going to have to address that contamination and also integrate into the existing environment. So all of that sounds a lot like legacy code, but there's one crucial difference. You can actually see it in this picture of an old rail yard. If you look closely, see all that leafy green stuff that's growing up between the tracks? That's because there are no trains running here anymore. So in urban planning, a brownfield property is no longer in use, it's derelict. But in software development, legacy code is still running in production, and that's one of the reasons why changing it can be so scary. So a support burden is one of the defining characteristics of legacy code. Your users depend on this code's behavior, and they're going to complain when that behavior is unexpected. And it's so easy to introduce new regressions here because legacy code's often unfamiliar. So we don't understand how it works or if it's fulfilling its intended purpose. We might not know what that purpose was. And whenever we have to change legacy code, we often don't know if we broke something until it blows up in our face in production. Finally, legacy code tends to maximize the cost of change because it's so highly coupled, both internally to itself and externally to its environment. So it becomes hard to change anything here without potentially affecting everything here. So this all adds up to a simple definition, really more of a heuristic for legacy code. Legacy code is any code deployed to production without tests. And it doesn't matter whether that was 10 years ago or 10 days ago. Now, I'm not the first person to define it this way. I'm not that brave. I blatantly stole it from this book, Working Effectively with Legacy Code by Michael C. Feathers. This was first published in 2004, but a lot of the advice in here is timeless. And it was really a formative experience reading this earlier in my career. So the author takes this definition further than I would. He says, code without tests is bad code. Yikes, dude. I mean, I would never say that about your code, sight unseen. But he goes on to clarify, it doesn't matter what the code looks like. Bad code is code that we can't change safely, and testing can help. So by this definition, you might have deployed some legacy code kind of recently, and you might be thinking, not my code. Or if you're more like me, you're thinking, not my code, not again. But once it's in production, untested code quickly acquires many of the same characteristics of legacy code. And this usually happens for reasons completely beyond our control as developers. The one thing that we can control is our tests. So let's look at how the cost of new code tends to grow when there are no tests. Maybe our company has a whole go-to-market process for new features. All of these marketing activities are going to increase user engagement, yay, right? But they also increase our support burden. The more users interact with our code, the more edge cases they're going to expose, which will then require support fixes. And as we make those fixes, the chances that we introduce a regression will go up with the risk of the unknown. So at first, the code's very familiar. We just wrote it. Then we start working on something else, and we dump that mental context until one day, we're looking at the Git blame for some particularly gnarly code, and we see our own name in there, and it's a surprise. So this process takes about 6 months max for me. But even when we still understand the code, there's an increasing cost of change. So let's step through a common scenario that many of us will encounter or have encountered. This is not a story from my current job, but in a way, it's kind of the story of every job. So suppose we deploy a new feature after a product manager approves it on staging. This is going to be a few days before the marketing launch because we want to get some early user feedback. And we haven't written any tests yet. We know we're going to be iterating on this again, so we're going to wait for things to stabilize. That early feedback leads to code changes. We thought it might, and there's a time crunch to get it done before the launch. So we don't have time for testing right now. We'll definitely get to it once the launch is out there. Except that's when our largest customer starts complaining really loudly. They're unhappy that this new feature does not support their extremely specialized use case. And so now, instead of writing tests, we're spending time hacking in some conditional logic to handle an extremely specialized use case. And as we deploy, we cross our fingers, hope we didn't break anything. We broke something, it was something important. And so now this is a production incident, and we need to deploy a fix immediately in order to restore service. So we're going to have to delay writing tests once more. All right, everything's finally stable. No one's complaining. It's time to sit down and backfill some test coverage. No, it's not. Now the PM wants to extend this feature with new functionality, and they expect it's going to be easy because our turnaround's been so impressive up until now. But now we've also accrued all of this technical debt, and so all of our changes going forward are going to be very expensive. So in the beginning, we started to climb this cost curve because of external factors outside the code. But by this point, the code itself is beginning to impede our ability to change it. So this curve I keep showing you has a name. It's named after a guy, Benjamin Gompertz. He was an actuary in London, and in 1825, he proposed this model for human mortality as a function of age. But eventually, people realized that this class of functions is even more useful for modeling organic growth. So the Gompertz growth model shows up in a lot of different disciplines, especially biology and finance. Many different things tend to grow and change this way. And it kind of makes sense that the risk of maintaining legacy code also fits this model. It grows organically because we created it and we're organic, and then we subject it to our own constraints. So what can we learn from this? Since this model is so widely used, there's been lots of research into optimizing it. In particular, it gives us a really good idea of when we should apply different testing techniques. So one possibility is that we could optimize the inputs. This is the function that I use to produce this curve. Changing the input values for any of these parameters is going to change the model. So as I reduce the value of the B parameter, for example, we still approach the same maximum, but I can change how quickly that happens. So you probably heard about flattening the curve earlier in the pandemic, and that's because the Gompertz model shows up in epidemiology as well. So this is essentially modeling the effect of writing our tests first. It's very effective. It's great if you can swing it. But legacy code already exists in production without tests, by definition. So these inputs are fixed. What else can we do? Well, this is one possibility. This downward zigzag models what happens when we iterate on our test coverage. So every time we write tests, the risk of this code will decrease at about the same rate as the original curve was increasing right there. But then the risk starts growing again as the rest of the system continues to change. So if we're diligent about writing more tests every time we touch this area of code, eventually the risk is going to drop to the point where it doesn't feel like legacy code anymore. This is the ideal. So every Gompertz function has an inflection point right here. And above this line, the growth rate starts to slow down. And this means the closer we are to this threshold, the more effective adding tests is going to be. This also happens to be the point where most developers start to realize that there's a growing problem with some technical debt in an area of the code. Might want to keep an eye on that. So here's a different model. We have a similar zigzag, but this one doesn't drop below a certain amount. So in this case, we started adding tests later, which means each round of testing is a little bit less effective than the first model. And because we're seeing less benefit, we're less motivated to iterate as often. And so the result is that we're maintaining equilibrium. We're investing effort, but the code's not getting any better. So there's another threshold right here. This is the tipping point where the technical debt became impossible to ignore. And so the team starts following that same good scout rule of we're just going to add some tests and leave the code a little bit better every time we touch it. But we're not seeing the same results anymore. So once we recognize that we're in this model, we've got two choices. We can either test a lot more aggressively. It's still possible to refactor this code into submission, but it's going to take a lot more intentional effort and planning. We can't just do it along and along as we do the rest of our work. Or we can accept that this code has an ongoing risk. So we'll write tests every time we need to make changes, but now our goal is just to maintain the status quo. We're not going to try to rehabilitate this code. And that is totally a legit option, depending on what the code is doing and what the priority is relative to the rest of your work. And so finally, this upward zigzag models what happens when we wait too long to add tests. I've done this a couple times in my career. At first, it seems like, oh, testing will solve everything. It doesn't, not always. So here we see very little reward, and we're trying to avoid touching the code as much as possible because it's so risky. And so that risk just keeps marching upwards. If you find yourself in this scenario, a rewrite might actually be cheaper than refactoring in place. Not all code is worth saving. I usually try really hard to avoid rewrites though. So the rest of this talk is going to focus on taking code from the danger zone, where Kenny Loggins lived in the 80s, and move it down to the comfort zone, where Kenny Loggins lives now. This is not Kenny Loggins. This was actually the first stock photo that came up when I searched for soft pants, because we're in the comfort zone. So let's say we've got some wildly dangerous legacy code in front of us, some Kenny Loggins kind of legacy code. And we want to get it into a test harness. Where do we start? Where do you even begin? How do you test the stuff that matters? Well, that's actually pretty easy. The only thing that matters is application behavior. It's the only thing that your users care about at the end of the day. This isn't any kind of formal process like behavior-driven development. There's really just one rule to follow here. The test should pass as long as application behavior remains unchanged. So focusing on behavior as opposed to just inputs and outputs will naturally influence how we structure our tests and the assertions that we choose to write. There's a model that I use to help me with all of this. It's called the seam model. If you're not familiar with this hand tool here, it's a seam ripper, and it's usually the first thing you reach for when you want to fix a mistake. So in software, the behavioral seam model is based on that same Michael Feathers book I told you about, and it's got a couple key concepts. A seam is a place where we can change behavior without changing code in that place. So this is going to be a logical boundary, and this is where we're going to write all of our assertions. Once we find that seam, we need to find the enabling points. So an enabling point is a place where we decide to use one behavior or another. And this is going to inform how we set up our test harness. So let's walk through a few examples. At the application level, users can directly observe behaviors along the seams, and we exercise these behaviors with integration tests. So this is the features board in AHA Roadmaps. It is a view for product managers to organize features into releases. You don't have to know anything about how any of this works. Just looking at it holistically, you can see there's a lot going on here. This page was very slow to load, and it was my job to make it faster. It also happens to be the most visited page in the entire application, so there was a significant support burden involved. And I wanted to give myself a safety net for refactoring, but I didn't even know where to begin. There's so much happening. So I went looking for smaller seams in this picture. And if we zoom in a little, each colored rectangle here is a feature card, and the rendering of each feature card is an application seam unto itself. So there's a set of behaviors here that will determine the card's final appearance. And there's an enabling point wherever we modify the underlying data. So if I update the status of this feature, then the background color of the card should change. If I assign it to another user, then the little avatar should change, and so on. Seams can also exist at the subsystem level. We use functional tests to exercise the behavior here. I concentrate on testing seams at this level the most because I do a lot of back-end development. One of my recent projects involved replacing part of the back-end for our internal analytics system. So we collect analytics data from all over the app, a bunch of different contexts. And they all get sent to this analytics tracker service, which will then enqueue a background job for each event on rescue using Redis. So the job logic that's executed by the workers is not important. All you need to know is that we had encountered a scalability problem with rescue and Redis in this area of the system. And so we decided we'd start asynchronously producing events to a Kafka topic instead. Now this could be an incredibly risky change. This analytics tracker is used in hundreds of places all over the app, and now we were risking potentially destabilizing all of them. So we decided to run both systems in parallel for a while and then cut over to Kafka gradually. And that way we could roll back easily in case we encountered any unforeseen issues. And to control this cutover, we used a feature flag. So feature flags are stored in the database, and they've got their own little administrative UI for managing them. So there are a lot of subsystem seams in this picture. Feature flags are their own little subsystem. Rescue and Redis are a subsystem. The Kafka producer and the broker form another subsystem. But for my tests, I concentrated on the seam around the analytics tracker and all of the application code that it uses in order to manage background processing. So let's look at the arrows that cross this seam. Anything that points towards the inside is an enabling point. So the feature flag model is where we decide whether we're going to send the data to either Redis or Kafka. All of the incoming messages to the analytics tracker are also enabling points, and any decisions we make here will change the shape of the event payload. And then the places where arrows point outside the seam are where we're going to write assertions about behavior. So this is where we're going to ask, did we send the expected payload to the correct remote system? That's the behavior we really care about testing here. And then finally, there are object seams. Object seams are exercised by unit tests, and we can draw seams around the public interface of any object. I tried really hard to find a meaningful example of legacy code that would fit on a slide. That was so not worth it. Basically, anything you've ever read about unit testing is addressing object schemes, and so I'm not going to cover them in detail. Other people have done it better. Sandy Metz is one of my favorite authors on this topic. I noticed this book's come up like a dozen times during this conference. Practical Object-Oriented Design in Ruby, or POODR, has an amazing chapter on testing that covers these kinds of object-level boundaries. So we talked about legacy code. What about legacy tests? Legacy tests break every time you change anything. If you add a fixture, the tests break. You change the name of an unrelated CSS class, the tests break. Sometimes you just look at it funny and a test breaks. So how do we prevent this from happening? Well, for answers, I look to that Sandy Metz book, and she says, from a practical point of view, changeability is the only design metric that matters. Code that's easy to change is well designed. And it's true, everything that you've ever learned about designing code was in service of changeability. If you never have to change the code, it doesn't matter what it looks like. It could be a fugly monstrosity as long as it continues to run in production. But code usually has to change eventually. And so she goes on to say, efficient tests prove that altered code continues to behave correctly without raising overall costs. So this is key. A well-designed test is a test that's easy to change, and efficient tests only need to change when the behavior changes. Together, this is describing high-value testing. So high-value tests prevent the most regressions and also have the lowest maintenance costs over time. Tests that fail when there aren't behavioral changes are low-value tests, and often when people complain that testing is not really worth the effort, they really mean that maintaining a suite of low-value tests is not worth the effort, and they're right. So what is test value? It's a combination of three factors. So when we're testing legacy code, our primary motivation is preventing regressions. There are lots of other reasons to write tests. This is why we write tests. This adds positive test value, and it's dynamic, so the test can continue catching more bugs over time. Then there's the initial cost of getting the legacy code into a test harness. This value's fixed. We only have to invest this once. And then finally, there's an ongoing maintenance cost to keep the tests passing, and this will continue to grow over time. And what's our unit of measurement? It's time. So bugs prevented is the time that we would have otherwise spent fixing them in production. It's gut feel. The initial cost is the time required to understand the code, to identify seams and enabling points, and then to create the test harness. And then the maintenance cost is the time required to change the test code in order to keep it passing. So there's one thing that's not on here, and that is the time it takes to actually execute the tests. When we're testing legacy code, the cost of changing code is always greater than the cost of executing the tests. If you get to the point where that's no longer true and you're really worried about how slow your tests are, congratulations, you don't have legacy code anymore. And that's when you can start to focus on speeding up your test suite. Until then, this is the rule that you need to keep in mind. So in other words, to prevent regressions, the tests must fail when the application behavior changes, and to reduce maintenance costs, the tests should pass as long as the behavior remains the same. This also tells us when we can delete a test. If it's easier to fix regressions than it is to fix the test is really not worth the effort. So, how do we write high-value tests? Well, focusing on behavior at the seams is going to get you like 90% of the way there. But it also helps to know a few pro tips. So first of all, integration tests. These test seams at the application level, and sometimes they get a bad rep because they tend to be kind of slow, and testing asynchronous JavaScript is just really difficult. However, they can also be the highest value tests in your suite by far because they catch the most meaningful regressions. So integration tests catch bugs that users would notice. The downside is that there is usually a large initial cost. It's much more expensive to set up the test harness because there's more code we need to understand, and there's usually a more complicated set of test data that we need to set up. The maintenance costs are going to depend mostly on our design decisions. So if we focus on behavior and keep our tests loosely coupled, then they're going to be more resilient and we're going to hold the maintenance cost down. So Creating the test harness, as I mentioned, is expensive, and it's going to be one of the hardest parts of any integration test. And this initial cost is just going to keep getting worse the longer you try to put it off. So one way that we can really help ourselves and our team is, for any code we write, make sure you set up at least enough of a test harness that it's possible to execute a simple happy path integration test. Even if you don't fill in any of the other test coverage, this is going to make it so much easier for the next person who touches that code. To reduce maintenance costs, we need to reduce coupling. And one place where tests can become coupled to each other is in shared test data in fixtures or factories. And we can get into this frustrating situation where just trying to change one attribute on one record, and then 5 dozen tests start failing somewhere else. Our change to the test data should always be additive in order to avoid this. So you can add new records, you can add new attributes to existing records. Anything else should be isolated inside a transactional test where it won't affect the rest of your shared test data. But even if we follow that rule, tests can still become coupled through count assertions. So when I write assertions, I like it to be a static literal, like this string. Expect page to have content for requirements. This keeps the test code really simple. It decouples it from the implementation. I don't have to know anything about how this is implemented in order to write this assertion. And this all works great, except when I'm asserting something that displays a record count. So if I use a literal for the expected value here, this test could break every time someone adds a requirements fixture record, even though the behavior didn't actually change. So I always pull my record counts from the data layer instead. It's a really simple thing, but it actually saves you a lot of tedium in terms of ongoing maintenance costs. So abstracting away selectors. Most integration testing frameworks allow us to interact with the browser by passing in a CSS selector or XPath selector to a finder. Then we get a DOM node, we can inspect it, we can trigger events on it. This is convenient, but it also tends to tightly couple our test code to our implementation, and we start writing assertions about the structure of the DOM or the HTML output instead of writing assertions about the application behavior. So one way to avoid this is to use any high-level DSL that your testing framework might provide. Capybara provides built-in helpers like click on, fill in, that read English descriptions of user behavior. But we can only use these helpers if we're testing an interface that's been designed for accessibility. They make certain assumptions about what they're going to find on the page, and most legacy code does not fit those assumptions. But we still have the power of abstraction. So here's an assertion that with a moderately complex selector in it. It's kind of long and dense. It wraps around to a second line, and we have to compare it against the rendered page to even understand what it's actually trying to assert. So it's looking for a card field with a flag icon that happens to be identified by this tooltip international expansion, whatever that means. So this assertion is describing the output. But what's the behavior we're really trying to assert here? Well, we can extract this into a more descriptively named method. And so now we've got expect page to have goal icon, international expansion. And so it's making an assertion that we've got this icon that represents a goal record that has a particular name. It's much easier to understand. It also means that we can reuse this method across other tests that might also interact with this UI component. And then the next time we have to change the underlying implementation, updating the tests is not nearly as painful. Basically, we want to make our main test logic read like a human language description of the behavior. So that's integration testing. Then we've got functional tests. These exercise a subsystem. It's units of code working together without going through the full stack. In Rails, controller tests are often functional tests. Tests for service objects are usually functional tests. In terms of test value, functional tests catch a lot of regressions. Not quite as many as integration tests. They're cheaper to set up than integration tests because the test harness is usually more focused. But the maintenance cost over time is a little bit higher, especially if your tests require any mocks or stubs, because you've now committed to keeping those updated. So functional tests are especially good for a couple different situations. One is if you want to exhaustively test behavior that has a lot of edge cases like error handling or user permission checking, the test harness for an integration test is quickly going to become unwieldy for this purpose, and functional tests are the perfect place for this kind of assertion. The other time is if you need to stub or mock any external resources. Integration tests don't always make that easy, and so sometimes it can be more convenient to write a functional test, which will let you expose more enabling points. And then there's unit tests. So a lot of the resources that talk about testing in general are actually talking about unit testing in particular. Both of the books that I recommended today are talking about unit testing. And there's just one problem with unit tests. It becomes apparent in this genre of memes that we'll call 2 unit tests, 0 integration tests. So you have these 2 doors which are both working flawlessly. Then there's the premature ejector. That's unfortunate. But it's still better than a vortex of microbes every time you wash your hands. They've got these Dyson hand dryers in the bathrooms here, and I've been thinking about this every time. The next one is my personal favorite. All right, wait for it. Ta-da! Works for me. And finally, there's this whole subgenre of corner cases encountered in real life. So these are all funny because they ring true. Unit tests are great, but they've got really one huge weakness. They are just not very good at preventing regressions, and that protection tends to fade over time. Meanwhile, the maintenance costs will also increase over time. Unit tests are coupled to our implementation at a lower level, and so often they have to change, even when the higher level application behavior that the users care about is the same. So low value doesn't mean no value. Unit tests are really cheap to set up, and at first they do catch some regressions. And so it's a very low-cost way to validate your design as you write new code. That's why I write unit tests every day. I know I said this talk was for people who dislike testing, but I lied. I write tests first. But long-term, the costs of unit tests can slowly come to dominate the benefits. And so the most important thing is only keep unit tests that are useful to you right now. It is never going to get more useful than it is right now. And since it's ephemeral, you don't have to keep it around because it might be useful to someone else in the future. As long as you have higher value test coverage that covers this code, don't feel bad about deleting old tests. And then the last thing is that, you can find literally decades of solid advice about unit testing, and it's important to know that you can also apply many of these same techniques to higher level tests. I learned about the seam model in relation to unit tests, but behavioral seams apply, at every level of the application. So, what have we learned today? We learned that legacy code tends to maximize costs, and it's usually for reasons completely beyond our control. Testing is something that we can do to minimize costs. For more resilient tests, we should focus on behavior instead of inputs and outputs. We should write high-value tests for our most important code. And finally, the test should pass as long as application behavior remains unchanged. So I'm out of time, but before you go, I just wanted to take a moment to thank my friend and colleague, Zach Schneider. Zach was really passionate about creating quality software, but he was even more passionate about creating an inclusive community. He attended the first version of this talk when I gave it as a lunch and learn at work last year. And afterwards, he pulled me aside and gently but emphatically encouraged me to take it to a wider audience. And so now here we are at RailsConf. I know your conference is almost over, but as you go throughout the rest of your day, please keep in mind that you never know when something that you say in passing might touch someone else. Be excellent to each other. Thank you.